All right. So, good morning. So today's talk is on the SDN technology, software-defined networking. This is not really a research talk like yesterday. This is more an overview of the technology, kind of some of the background, why it is important. Describe what is different between this technology and current state of affairs. And there's a couple of reasons why I want to give that talk. One is, of course, this is a relatively new area, and there's a lot of ongoing research. In fact, the number of conferences dedicated to SDN and network function virtualization and so on is increasing every year. And the second reason is that we have actually received here a grant from CACST to build a SDN prototype, and this we were notified that this grant was approved back in, I think, August or September of last year. I don't think the funds are already here, but once the funds are here, then there will be a kind of a state-of-the-art SDN facility that is both a test bed, a physical test bed, as well as simulation software. And then it will enable a lot of potential work and research in this particular area. So, hopefully there will be some knowledge here that can build upon that and use the prototype. So I'll talk about, as I said, some of the background, why this was, what led to the development of SDN. And I'll talk a little bit about SDN architecture and the open flow technology. And again, this is, as I said, well-known information. It's just I'm presenting it in my own way, but there's no real research topics here. Okay, but I'll discuss some research topics at the end once I've given an overview of the technology. So, if you look at today's network, right, you have IP forwarding. And we all know that this is best effort. It's also egalitarian. I'm going to talk about that in a moment. And there's been a lot of calls to overcome this network ossification. And this ossification is due to four reasons that I've listed here. And I'm going to expand on each of these issues in slides in a moment, okay? But basically, what you can see is that if you look at how networks are built today, they're built with proprietary systems, okay? So you get Cisco equipments or Juniper equipments and so on. We'll see what are the equipment trends that are leading to this ossification. The system, the network is a fully distributed system, okay? So you have, let's say, OSPF or ISIS running, and it's running at each and every router, and the router will have to talk to all the other routers to collect information and so on. So it's a fully distributed system. And the way that, the analogy that many people have come up with is to go back to the years of mainframes, okay? Back in 30 years ago, when you have mainframes before the advent of personal computing. I'm going to show you the analogy in a moment. So I'll look at each of these five bullets in more detail in a moment. Okay, so we know that IP forwarding is best effort, or as some call it, is send and pray. Okay, but it does work very well. Okay. It does work very well. Nevertheless, it's also egalitarian, okay? The routing is based only on the destination address, nothing else, okay? So it doesn't depend on the packet content. It doesn't depend on who sent the packets, okay? But the reason that this was adopted, of course, is because now at each router we'll only have one entry per destination address, as opposed to one entry per source times destination address, or one entry per packet content type times destination address, and so on. Okay, so it allows scalability of the routing tables inside the routers. Okay. The other thing is, as I said a moment ago, is that the forward decisions are made in a fully distributed manner, right? So the way, for instance, OSPF works is that a router will collect topology information from all the other routers, and then it will run a local version of the Dijkstra's algorithm, the OSPF algorithm, and will determine the next hop forwarding decisions. Okay. So if you are a network engineer, a network operator, and you would like to know the paths, okay, it's not possible to figure out the paths unless you collect information for from each and every router on the network, okay? And if you just stay with that OSPF routing paradigm, it's not possible to do any traffic engineering, okay? So these are obviously limitations, and of course people have addressed it. Okay, so traffic engineering really means that the network operator should be able to control the paths that the packets take through the network. Okay, and potentially an operator would like to select the paths based on the type of traffic, okay, based on priority that is assigned to packets, you know, based on the source. Okay, if I've paid a lot of money to the operator, maybe I want my packets to get a better treatment, take a faster path, and so on. Okay, or it could be just plain load balancing, right? I mean, the network operator may want to optimize the use of its own resources, so they want to just do the load balancing. So how can you accomplish this? There are only, generally, so far there have been two ways to do that. One is to use connection-oriented networks, and the other one is to use routing overlays. Okay, so let's look at this. So connection-oriented networks, you can use ATM, for instance, or X.25 and so on, okay? And the way that this works, of course, is that each switch will have a set of policies configured by the operator, and then you have to, before you send any packets, you have to do a connection setup. The connection setup goes through each and every switch, and so now you have complete control over the path, okay? And you have complete control over the path, and you can assign any resources to the connection based on all these factors here, okay? So different connection requests will get different priorities, will get different paths, different bandwidth, and so on and so forth, okay? So, again, you know, there are examples of networks that have used this approach, and the nice approach of this is that because now the decision is built inside the switch, okay, it can be done in hardware, okay, and so you can support very high data rates. It doesn't involve the running of software and all that, okay. But of course there are disadvantages here. It's connection setup and the state. Okay, so it's very expensive instead of in terms of the amount of state that the switches have to maintain. So that's not scalable, and so it's not surprising that ATM never conquered the world. Back in the 80s, there was a lot of late 80s, early 90s. There was a lot of work on ATM architectures, and you know, there was high hopes in terms of ATM becoming the dominant protocol. That never happened, and cost and scalability were the main issues there. Okay, and despite the fact that IP did not offer any of the quality of service considerations that ATM has, because it's so much cheaper, and it does something. It does what it does very well, right? So an IP network does one thing, but it does it very well, and that is fast forwarding of packets. Okay. And so it won. Now, and then you have these routing overlays, okay? And so what you can do is you can leave IP, and IP can work the way it does for most of the traffic. But if there is certain traffic that you want to treat differently, then what you do is you set up a routing overlay. And MPLS is an example of a routing overlay. Where basically what you do is you build tunnels between routers, and these tunnels are, you know, can be thought of as virtual point-to-point connections, okay? and now you can forward your packets over those tunnels, okay, but of course then your routing is limited to the tunnel topology, which is the virtual topology, okay. So it is very fast because now it's label switching, so you set up your labels in advance, okay, for your traffic, and then once that the MPLS packet goes to the router, only they have to do the lookup. It's very similar to the way that ATM does it, right? So it can be done in hardware very fast, okay? The overlays are flexible. You can change them anytime. You don't have to change the topology of the network, but you can easily change the topology of the virtual network that's running on top, okay? And if you have different types of traffic or different customers, you can basically use different overlays. So now you have a single physical network, right? But then you can create multiple virtual topologies or overlays on top of that to segregate the traffic that you carry. Okay. So MPLS is widely used in the internet today. Okay. It has been used for the last 10 years or so. So this is a well understood solution. Okay. But it's not a very good solution because there are some drawbacks to that. The first thing is that the overlay and the physical topology operate independently, okay? So what this means is that if there is a problem or a change in the underlying physical network, okay, this is not immediately reflected in the virtual network. So now, supposedly, you picked a virtual tunnel because of the cost or the delay on the underlying routes, okay? But if this cost or delay in the underlying routes change, then your tunnel may not be optimal or may not be a good solution anymore, okay? So you have to rerun that, and it's not done automatically. So anything that changes at the physical layer or the routing, the physical infrastructure that is not reflected automatically, okay? And so then you can have inefficient routing in the overlay. There's this other effect as well, okay? The effect where you basically route a lot of traffic over the virtual network, and by virtue of doing that, you change the parameters of the physical network, right? So there's kind of an interplay because they are run independently that a change in one is not reflecting the other and vice versa, and you may actually create a kind of a vicious circle where you change the way the traffic that you put in your virtual network, that changes the weights in the underlying network, that OSPF reruns, finds different paths. Now it becomes, your virtual network becomes suboptimal. You change that. By changing that, you change again the underlying network. So there's a lot of issues that are there, and by running these two independent networks. Okay, so all right, so that's one issue. Okay, now let's look at some other trends. So as I said, generally networking devices are running with proprietary software and proprietary hardware. Okay, that again going back 30 years, this is how mainframes used to run. Okay, you would buy a big machine from IBM. Okay, it will come with its own, its own proprietary hardware, and you would need to train your people to use its software. Okay, this is exactly the same way, and there's a couple of reasons why it's done so in this manner. One is intellectual property. Okay, so you want to establish your intellectual property and get patents on the hardware and all that, and that means competitiveness, right? So no one else can do what you've done unless they pay you royalties and all that. So that establishes the competitiveness. The other thing is that by tying hardware and software together, right, you can make it more efficient because they're designed to work together, okay? But there are severe drawbacks, okay? The severe drawbacks is that the only one who can make changes, okay, is the one who sold you the software and hardware, right? So if you buy something from Cisco, okay, it's working well, but let's say that you want to make some modifications, some changes, something that is particular to your network, okay? The only way to do that, you can't touch the Cisco hardware or software, right? So the only way that you can do that is you go back to Cisco and say, I'd like you to implement this for me, okay? And they go back to their lab, they implement it, and 6 months or 9 months later, you have a solution. By that time, your requirements have changed, right? And so it's very slow, progress is very slow, and it's a very high barrier to new ideas, right? So if you have an idea today, you can't go and implement it, okay? You have to go through the vendor and go through this cycle of back and forth. And of course, there's non-standard interfaces to hardware. They're customized, for their own software, for their own solution, okay? And so it's a problem because if you want to change something, you have to change both the software and the hardware sometimes to do that, okay? Network equipment, what happens is that you have typically custom ASICs, okay? And that's because you want it to run very fast, right? And you want it to keep up with the growth in traffic and network capacity. So, but because it's hardware-centric, hardware always has a slower innovation cycle than software, okay? And it has reduced flexibility. You build it for a specific purpose. It's difficult to, you have to redo the ASIC from scratch if you want to do something else, okay? So there are issues there. So now we put all of this together. So basically the way it works in today's networks, right, it's like this. So this is a router. So it will have customized hardware, okay? We have customized operating system, okay? So iOS, let's say Cisco's iOS, okay? And then there are these features that the vendor implements, and only the vendor implements, okay? And these are the features that the customer requests the vendor to update and so on. And this is basically replicated everywhere. And typically a solution will be that you have the exact same configuration at every box that you buy. If you buy equipment from different vendors, then you have to make sure that they can talk to each other. And so there's all those compatibility tests that you have to run, and it's not a straightforward solution, okay? So typically, if you buy your equipment for a vendor, if you buy your equipment from a network, it will be from the same vendor, and typically you are also locked to that vendor for years, okay? And it's totally distributed, as I said, so that the boxes will have to talk to each other. The operating system here will talk to each other to figure out topologies and topology changes and all that, okay? So this is, as I said, very similar to the way that it was done with mainframes. And in fact, if you look at the racks of equipment, they're very similar to the old mainframes, okay? So big boxes that fit a room and all that. So you have things like this. So, everything, routing management, mobility management and all that, this is done there. And you have millions of lines of source code. Think about the number of RFCs that you have to support, right? So there's probably about 6,000 RFCs right now that have to be, not all of them, of course, are supported. Okay. Custom hardware, and so it's basically a vertical integration, okay? Now, so here's the issue, right? Suppose that there's an update on an RFC, and so now your software here has to be updated to support that RFC. Well, you have to change it everywhere in your network. Okay, on every box in your network, you have to implement that change. So it's not a single point where you have to update. It's basically every router in your network and possibly every switch, depending on how your network is built. Okay, and so this is the kind of problem that SDN is trying to solve. Okay, what it's trying to, it's basically a hybrid approach where it says, I'm gonna combine this connection-oriented networking and routing overlay topology. So remember I said, there's connection-oriented and then there's the overlay. I'm trying to combine the two, okay? And what I'm gonna do is I'm gonna use hardware as much as possible, right? Because I want the forwarding of packets to be very fast. So classification and routing will take place in hardware, not in software, okay? And in other words, I'm going to use a high-speed forwarding hardware, okay, which already exists, okay, not software. However, I'm going to try to avoid using routing protocols which by definition are distributed, and I'm going to allow the network manager to specify how to handle its flow. Okay, so I'm going to give the manager this capability. I'm going to take it away from the routers, okay, and also allow for management applications to configure and control the network, not humans. So you know, humans should not have to go in and check the boxes and all that. So let's see how this can be done. Okay, so this is the analogy that I showed earlier. So remember what happened with the mainframes, right? You had specialized hardware, operating system, and applications, okay? It was basically vertically integrated. It was closed, proprietary, and slow to innovation, okay? Then what happened in the 80s? What happened was this separation of these three domains where you have an Intel microprocessor that can run pretty much any operating system, okay? So you have Windows, you have Mac OS, you have Linux, okay? These are the three main ones that are used, okay? And now you have, and so the way that it was done was by using open interfaces, okay? So the Intel processor had open interfaces that can be accessed by the different operating systems, and then each operating system offers open interfaces to application writers, okay? So now what you have is that, you know, obviously now you can innovate in all three layers independently of each other, right? As long as you make sure that the interfaces are open, you can make your, you know, Intel can make its upgrades to their processors, okay? You know, Microsoft and Red Hat and Apple can make the updates in their operating systems, again keeping the interfaces open. And then obviously now you let everyone, pretty much everyone, be an application programmer, okay? So any of you can write, for example, code for the Android store or the Apple App Store and actually make money out of that, okay? And of course, not just that, but obviously also for any operating system, you know, even for PCs and all that. So now it's very horizontal, open interface and rapid innovation, right? So if you want a new application, well, and it doesn't exist, well, you go and write it, okay? You don't go to Apple and say, can you please write an application for me that does that, all right? So that's the beauty of this. And so now, so SDN is basically taking that one step further, not just at the OS level, but also at the network operating system. So what we have here is, again, a vertically integrated industry, okay? You buy from Cisco, you buy from Cisco the whole package. You buy from Juniper, you buy from Juniper the whole package, okay? But now, what you have is, you have off-the-shelf switching chips. So anyone who doesn't, you know, just whoever manufactures Ethernet switching fabrics, for instance, okay, can provide this. All they need to do is make sure that they do fast forwarding at wire speeds, okay? If they can do that, then this is fine. Then, now you open it up to have a control plane, okay? And I'm gonna, so control plane, so I'm gonna also call a network operating system, okay? And then on top of that, you can write applications. So as long as you keep the interfaces open, then this whole thing becomes horizontal and you can have rapid innovation. The innovation can happen again at every level, okay? Obviously, most of the innovation will happen here, right? Because yes, the switching chips will improve over time, just like microprocessors do, okay? But that is probably a slower pace of innovation than what you need to do to manage your own operation, okay? And that will be happening at the software level, okay? So
I can understand.
Sure.
I can understand it like this. The operating system itself will be shifted up. I mean, for Cisco, for example, the iOS will be moved to this control
Yes. And it will be moved out of the boxes. I'm going to show you in a moment.
So.
Yes, right. So actually, that's a good segue into this figure, right? So now, all you need is some dumb hardware, okay, that the only thing they do is forward packets very quickly, okay? It's a very, very fast switching fabric. That's all it is, okay? It doesn't do any software, any complicated, I mean, obviously, everything has to do is have some software, right? But it doesn't do any of the routing or features that are applications that the routers do today. Okay, all they need to do is just be very simple. Simple means it's easier to implement, can be implemented and do the work faster, and have an open interface between itself and the network operating system. The network operating system, okay, and there's actually many of them already, and I'm going to show you a slide on that, okay. It's not even running at the boxes anymore. It's running outside the actual network. It's running on a controller. I'm going to show you that in a moment. But it talks, so that controller will be talking to all the switches so that it can collect information, important information about topology, statistics, and things like that. We'll get to that in a moment, okay? And then, once you have this, and you have a well-defined and open API to the applications, then you can write your own features for your network. You want to do better routing algorithm. Let's say you came up with a better routing algorithm, okay? If I have this picture here, okay, good luck introducing the routing to the network. That's the reason for this ossification that I talked about at the very beginning, right? You have to go to Cisco, prove that it works, have Cisco implement it, Cisco introduce it in its boxes. You know, it's going to be years before anything happens, right? Now you have a good algorithm. You think that your algorithm is going to be better than what's out there. Fine, write an application, test it on your own system, implement it right away. Okay, as soon as you write it, it's ready to implement. Okay, so I'll get to that in a moment. So, and this is now where the main idea here is that typically what you have is an Ethernet switch, for instance. You have the data plane that handles the packet processing, the switching fabric between the input-output ports of the Ethernet switch, okay? And there's the control plane, which is basically a management interface to control and configure the device. And so really what you have is you have these two pieces that are running. So this is the hardware part, which is determines the data path, okay, data plane. And there's the software part that is the control plane, okay. And so with this, with the SDN architecture, what you do is you take that control path software out of the picture completely, okay? You move it over here at the top, okay? Yeah, as an application, correct. So, so you can think this is another way of thinking about that, okay? So this is now the control plane, and this is the data plane, okay? This is just data forwarding, okay? And although I've said here OpenFlow switch, OpenFlow is just one example. I'm going to get into that. So assuming that it runs an OpenFlow, the OpenFlow protocol, then it's an OpenFlow switch. And so now any routing, traffic engineering, or any other applications that you want to do, virtualization, multicasting, you know, anything that you want to do, you can implement it here on top of the network operating system, okay? So what is the network operating system? No, this is a distributed system, okay, that creates this consistent up-to-date network view. This runs on servers, and these are called controllers. So in the context of SDN, these are the controllers, okay? And there's a number of operating systems already. Probably the most famous one is Nox, okay? There is a lot of activity in this area. I don't know if you've heard about Nistica. Nistica is the company that was founded by some Stanford folks who actually came up with the OpenFlow idea. Nistica was sold to VMware for a couple of $1 billion, maybe 12 to 18 months ago, okay? And there's a lot of activity beyond Nistica in terms of startups in this area. Okay. All right. Now, so the network operating system, as I said, it will talk. Any questions? So the network operating system is fully distributed because it talks to all these switches, okay? And now the question is, how does it talk to the switches? Well, there have to be some API to do that, okay? And to build this API, you need this forwarding abstraction. So, each network OS will have its own network forwarding abstraction, okay? So that will depend on the particular operating system. So the forwarding abstraction basically is used to do two things, okay? One is to get state information from the switches, okay? The state information will tell the controller, what is the status of the switch, what devices it's connected to, statistics about the traffic that it has received and all that, okay? And it then gives it a way to talk to the switch and give it commands, okay? Directives, okay? So this is what you need to do. And I'm going to talk about that again in a moment. Yes? Yeah. Sure. Correct.
Okay. Now that there is no logic in the forwarder, okay, without, okay.
Mm-hmm.
But the controller definitely, in order to forward a packet or in order to dictate a flow to the forwarder, the controller does need a feedback from the forwarder because the packets are coming to the forwarder.
Right, right.
So unless until the forwarder will inform the controller that what type of packet I am receiving, how the controller will come to know that what flow I have to dictate to each forwarder. So if we have removed the logic from the forwarder, so does it mean that it is simply a hardware now? As from the data path, we have only the hardware.
Yeah.
So still there, it does need a sort of iOS or something which can, through which it can dictate to the controller that what type of packet I am receiving, so that controller can decide the type of the flow, and it can dictate the flow entry which the
Right. This is absolutely correct. So what I mean here, this is the traditional or the conventional control plane software that is there. You are absolutely right that you need to have a small piece of software, and I saw that in the, I'm going to show you this picture. So basically what you do is, whatever was there, because, the people who developed the OpenFlow also thought about how to evolve from the current state of affairs rather than just having a completely new solution. So the way that you do that is whatever goes there, you don't touch it, that's fine. The only thing that you do is you install what is called a lightweight client, OpenFlow client. So I'm going to get to that in a moment. So that allows you to talk to the controller, okay? So you don't take it completely out, but basically you have a very lightweight software that allows you to talk to the controller and pass this type of information. So I'll get to that, okay?
I am now going to dispense with all the previous control flow software.
I'm sorry?
I'm going now to use the small client and dispense with all other software.
Yes, inside the switch, yes, right, yes. All you have to do is, so, for old switches that did not support OpenFlow, all you have to do is just go in and add the OpenFlow client, okay? Now, but many vendors now actually support OpenFlow, and so if you get a new switch, right, that will most likely also include this OpenFlow client itself, and then, obviously it can update itself to the newest versions as they become available. Yeah. So let me see where I was. Okay.
One more question.
Sure.
Previous slide. Here, as we said that we have removed the logic from the forwarder, we brought it to the control plane. Now on the control plane, we still have a control program A, B, whatever are the controller programs are there.
Here, yes.
Network OS, where the network OS is basically running, right?
Controller. the controller.
It can be Linux or Windows.
Yes, it can. Yes, yes, anything. Yes,
Because
it.
the control program we have to run on a hardware.
Right, right. So the yes. So as I said, the it's typically not Linux or Windows. Okay, it's its own operating system. It's a new operating because it doesn't do what I mean. It's a specialized operating system for the network. It's not for a machine. So you can't just take Windows or Mac OS or Linux and run it there. Okay. You have to have a specific, so a controller now becomes, you have to identify it with a vendor. Just like when you buy a laptop, you have to make a decision. Am I going to buy from Microsoft, a PC, okay, from Lenovo or HP and so on, or I'm going to buy a Linux from Red Hat, or I'm going to buy a Mac OS, okay, from Apple. Correct. So the control program, now think of that as an application.
That is a traffic engineering application.
Yes, no, it can be anything. It can be just traffic. Yeah. And so the network operating system may actually come with some applications already built in. It may come with the traffic engineering application. It may come with the routing application, okay? But then you may change them. If you don't like what they do, you may write your own. If you have a software team in your network that can do that, you can write your own. Does that make sense?
We can write our own operating system or control program.
You can do both. You can do both, right? I mean, just like Linux. Linux was developed by freelance programmers, right? So if you want to write your own network operating system, you can do that. Yes, the hardware itself is just a simple switch. You mean the controller hardware? Yeah, the controller hardware can be any, an Intel, you are right. So the controller. So let me take it back. Yes, so the controller itself will be just like a PC. Okay, it has to be. It has to, have a CPU, an operating system, and so on. Then on top of that, you write your own network operating system. Yes. Okay. Right. So, right. And so the control programs now. So again, I'm going to. So this is distributed. This part is distributed, right? Because it talks to everybody. But these are centralized. They don't, these applications are centralized applications. They take whatever, so the network operating system will connect will get the global view and will have it locally, okay? And so all these applications, the control programs, do not have to do anything that is distributed. They have everything there, okay? And they can be run in a centralized manner. So you basically take as input the global network view as a graph or a database or however the network operating system presents that to the application. And then they decide what the switches should do. Okay, so that's the whole point, is now you can figure out what the switch is, what you want the switches to do. So if you want for a particular flow to take a particular path, you have to go to those switches and program them to forward the packets of that flow in a particular way so that the flow will follow that particular path in your network. Okay. So the control programs, again, this is the important thing, is not a distributed system, and so it's easy to write, okay? It's difficult to write a distributed system that you have to install in tens, dozens, or hundreds of routers in your system, but it's very easy to write a centralized system that runs on a single controller, okay? And so the whole point is that the network operating system abstraction hides the distributed nature of the system from the control programs that program the switches. Yes.
This would indicate that the topology of the network will not be dynamic.
No, it can be dynamic.
It will be before it started. We have to establish the topology. Once the topology is fixed, saying the data controller can
No, no, no.
can we change the configuration?
Yeah, you can,
during running?
absolutely, yes. And so, again, the point,
Distributed.
no, but the point, no, it is, no. These guys don't know it is distributed. The topology is distributed. It's just that the network operating system will hide it from the programs, okay? But the network operating system, that's its job, is to talk to the switches and find out, did the switch go down, okay? Did a link between switches go down, okay? So it will learn that. As it learns that, it updates the topology, okay? And therefore, now these guys will have a different topology to work with. So yes, it is possible, okay?
The real drawback basically is that if this control goes down.
Yeah, we'll get to that, sure. Okay, so this is how routing is done, okay? Basically, you have today, okay, on this left side. So today you have, this is a router, okay? The router has the OSPF protocol. The OSPF protocol has a distributed way of collecting information from all the other switches in the network, and also to disseminate information from its own state to all the other. Okay, so it will have this part, that's the protocol part, and then there's the algorithm part. So, once you run your protocol, you run it continuously, you collect the information from all the network, then you run your Dijkstra's algorithm on top of that, okay? And then it has an operating system and custom hardware, and this is replicated in each and every switch in the network, right? Here, the way that you do it is like this. You have the packet engines, okay? These are dumb devices, right? They don't do any software other than talk to the network operating system. The network operating system collects that, so it's a single point where you collect that information. And now you can have different applications running. And so the point here is that you have the option of doing OSPF or OIS, okay? Or RIP or whatever it is. But once you choose that, then every node in your network has to choose OSPF. You can have some nodes speak OSPF and some nodes speak ISIS or RIP, right? So you either have this or you have that. You can make you can change that dynamic. You have to shut down the network, change the routing algorithm and do that. Okay, here you don't have that problem. Why? Because if you're gonna make a change, let's say you decide today that you don't like OSPF, you're gonna do ISIS, all you have to do is just flip a switch, and instead of using this application, you use that application, that's all. If you don't like neither of these, you are free to write your own routing algorithm, okay? If you don't want to do shortest paths, but you want to do something else, well, write your own algorithm and just switch it here, change it here at the controller. The packet engines will not even know that there's a different algorithm running here, okay?
Why we cannot do it on the existing system?
Huh?
Why we cannot do this with our existing systems?
Without?
In the existing system?
Yeah, you can do that because all the switches have to talk the same protocol, right? If a router wants to find information from other routers, they better use the same protocol, otherwise they cannot.
For individually, you can go to individual protocols and follow this.
No, you can't do that.
I can say something that there's redistribution between protocols which exist even now in the routers.
I'm sorry?
There is redistribution from one protocol, routing protocol to another, which could be configured between different protocols. How is that different from the SDN approach?
Yeah, the main difference is, of course, that even if you were to do that, you have to do that at every router in your network, right?
Translation.
Huh?
That's what I said, actually. That's what I said. I said, can we individually do it on every?
If you have a network which is running OSPF, and let's say the other network is running RIP,
No, that's right. That's a different network running ISIS, right?
Okay.
That's not what I'm saying here. I'm saying the same network, right? So my point is, maybe I misunderstood your question. If I have one network that runs OSPF and another network that runs ISIS, I have no problem. This work together. Okay. Huh?
They are talking the same language.
Yeah, no, so remember, OSPF is within an autonomous system. Autonomous systems are free to pick their own routing protocols, okay? So if KAU wants to run OSPF, they can do that. But then they connect to the rest of the internet, and if the autonomous system next door wants to run ISIS, that's absolutely fine. The reason is the way that they talk to each other is through BGP, because they're going to connect to the rest of the internet using a BGP router, and the BGP router has to be talking to BGP, right? That's the only thing. What I'm saying here is, let's say KAU decided that to change their own protocol from OSPF to ISIS. The only way to do that is to go and change each and every router. And by the way, while the routers are running, you have to basically take down the whole network, because if I change the protocol in router A and router B, which is connected, is running OSPF, the other one is running ISIS, they can't talk to each other anymore. So my point is that within the same network, I can change from one protocol to another by just changing the application here. That is not possible to do today. I'm not talking about different networks, I'm talking within the same network.
Maybe we should discuss further.
Okay.
But if in a router I have two routing protocols running at the same time, is that a problem? Right now, in the existing system?
Yes, no, it's not a problem. I mean, you could have potentially do that, but only, yes. But then you're running two protocols, that means twice the overheads. But now, here's the question. If the two protocols come up with different views of the data, of the topology, you have to decide which one to use. So de facto, you have to use the topology of one protocol, not both of them, right?
So can we do both at the same time in the SDN? Two protocols running parallelly at the same time?
You can do that, but again, only one of them will be allowed to change this.
I believe finally the net result is the same. It looks like the outcome they're going to use one single protocol at a time.
No, that's absolutely right, okay? But, as I said, typically you don't do two routing protocols because there's additional overhead. Here there is an additional overhead, okay? And second, in order to change from one to another, it's much more complicated to do. I'm not saying it can be done. It's much more complicated to do here than to do it here. Yeah, obviously only one routing protocol has to be in charge. There's no question about that. Okay. Yes.
There is a thing that is called administrative distance. Every routing protocol has administrative distance. Based on that, the skills vary. Either it is running multiple protocols, no problem.
Right.
But based on the administrative distance, it will behave the same.
And I understand that. Okay. Yes.
General question
Sure.
related to SDN.
Mm-hmm.
Generally, in the management, in order to manage some organization, we delegate the powers at the lower level. So if we assume that the forwarders are the lower levels of the employees, the powers are going to be delegated from the higher management to the lower management. Here, what we are doing opposite to that. We are taking the powers from the forwarders and we are centralizing it at one place in the
Right.
network.
Right. Yes.
So is it not against the management rule?
No, actually, remember what I said, that you want to be able to control the paths. The only way to control the paths is to actually take the power from the routers and put it at a centralized controller or manager, okay? Because again, so that's the other thing that I want to mention, okay? So yes, here you can have only one protocol. So actually, I'll take back what I said before, which was that you only can have one operating system, one routing algorithm working, okay? And here's why. Because if you, let's say you have OSPF here, right? And you may have 10 routing protocols, but only one is operating at, running or making the decision at one particular time, okay? Now, if you're basically limited to the decisions, you are limited to the decisions that this protocol is making. So you can't go and say, okay, but if I want this type of traffic from A to B, I want it to take this specific path. You can't do that. You have to basically take whatever OSPF does for you.
Override it by writing a protocol which has a better administrative distance, like
No, they have to change the distance. No, you can change the weights, That's right. But then OSPF takes the weights and does
If I
that.
put a static route, it has powers better than the OSPF.
Correct.
It can take over.
Yes, that is true. Okay, absolutely true. But then that typically requires manual intervention, right? And then setting, the paths throughout the routers. Okay. What I'm saying here is the following. I can say as a manager, I can say that I can have a hybrid protocol that says I'm going to take what OSPF gives me for every route, but if there's a flow that goes from A to B, I want you to take that route. Okay. And that protocol, you only need to change it here. You don't need to go and change it on every route. Okay? And you can do that. Okay.
Actually, one of the hack I proposed to my master's student, because he had problem to configure that. I said, if we fail to do it, then worst comes to worst, we write a bot that will go and change static routes.
Right. Yeah. So, right. Yeah.
So basically, what I see.
But okay. But the thing is, okay. So look, there is a lot.
It's
Go
like
ahead.
better architecture, more force architecture.
Right. Yeah. The point is that what is the source of most of the errors in the network? It's not hardware errors or software errors. It's human errors, okay? A human who will have to go and set a static route, it's very likely they're going to make a mistake somewhere, okay? And then you're going to have to figure out what went wrong, and it's actually a lot of man hours figuring out, okay? So the point is that not that you can't necessarily do all these things today, is that you have to do it manually. Most of the time it has to be done manually, okay? This takes that away, and again, as I mentioned earlier, you don't want the operator to go and manually change things, okay? You want to have a centralized system, and if something goes wrong, you can immediately debug it because it's sitting right there. You don't have to go and check the state of all the switches and figure out where the error happens, okay?
This is the purpose that we are going to minimize the manual configuration, and we are going to automate the
Exactly. Yes. Okay. So, all right. So now that I've talked about this, so the important thing is the forwarding abstraction. And remember, what is the forwarding abstraction? The forwarding abstraction is between the network operating system and the switches. Okay. All right. So what you want to do, just like with microprocessors, you want to abstract away the hardware features. Okay. And you want this to be flexible, so it can be specified by the control plane, and it has to be used by a basic set of forwarding principles. So think of that as the instruction set of the microprocessor, right? So these are the instruction sets that you use to tell the switches what to do. Okay. So they have to be, obviously low power today is important. It has to be quick, and it must not be vendor specific, right? So it has to be open. Okay. OpenFlow is an example of that. Okay. There's other protocols, but OpenFlow is the most popular one that supports this abstraction. And SDN is not OpenFlow. OpenFlow is just an open API that can be used to build SDN networks. If you come up with a better abstraction, that's fine. I mean, get an RFC, and other people may implement it. Okay. And so basically, it's the standard interface for programming the data plane switches. So again, this is what it is. So you basically have open flow between these two that decouples the control logic from the data plane. And so it basically runs between the controller and the switches. And this is what I said before, which is that, whatever was there at the controller, you don't use it anymore. The switch, you don't use the control path software anymore. You install a simple OpenFlow client that talks to the OpenFlow controller over a secure protocol. So it's always running over SSL, because obviously this has to be secure. Okay. And then this translates the commands that it gets from the OpenFlow controller. So now there are two things, right? This part is not vendor specific, okay? It gets the commands, and then the OpenFlow client is, of course, vendor specific, right? Because every Ethernet switch or switch is built by a different vendor. It will translate the OpenFlow commands to specific vendor-specific commands to make changes in the hardware configuration. Okay, so that's the purpose of the OpenFlow client. So here's an example. Okay, an example is that if the header is P, send to port 4. Okay, so there's a flow table inside the switch. So the switch will look at the header. If there is a match, okay, it will take that particular action. If the header is Q, overwrite it with R, add S, and send these ports 5 and 6. Okay. If this is an unknown header, okay, send it to me because I'm going to see it. I'm going to inspect it. Okay. So because again, the switch itself can't do anything, right? It can only do matching. And so if it says, you know, if this is an unknown flow, let me take a look before I decide what to do with that flow. Okay. So the OpenFlow primitives, yes.
These things already exist in ATM, ISDN, and all these things. What is different between, like PCI is there, which takes decision depending upon the flows. So what is different here?
Yeah, what is different?
ATM, ISDN, all these technologies.
Right. So it's not different, okay? As I said earlier, the point was not to make them different. The point was to make the separate the control from the data plane. So the headers and all that. So I mean, this is meant to work with existing technologies. I mean, it could be ATM, it could be Ethernet packets that are sent, it could be IP packets that are sent through. So I'm not saying that there's anything different in that respect. What is different is that this technology takes the connection-oriented technologies like ATM and so on, X25 and so on, okay? And then it makes it possible to make the decisions in a centralized manner outside what is currently called the control plane, the network. So it separates the control plane from the data plane. That's what it does. Today, switches have to support both. This takes the control plane decisions from the network, puts them outside. It only leaves the data plane decisions in the network. That's all it does.
Do you think it is really qualified for real-time data manipulation?
What do you mean data?
And large payload transfer?
Yeah, sure, yeah, absolutely. Let me show you an example of how it works, and then we can discuss some of the details, okay? So this is basically, so the OpenFlow primitive is like this, okay? So it basically does two things, okay? So this is the commands that are exchanged between the switch and the controller. They have a match and an action, okay? So basically you match arbitrary bits in the headers, so you can have a mask that says match these fields, okay? So it has to be a 1 here, a 0 here. Here I don't care, then a 0, then a 1 here, these two I don't care what they are, okay? So if there is a match, then do this particular action, okay? And so, and now this mask allows for any flow granularity, okay? It could be just a single flow, it could be an aggregation of flows, it could be anything, okay? I'm gonna get to that in a moment. And then the actions that are supported by OpenFlow is forwarding, dropping, send to the controller, override the header with a mask, push or pop headers, just like MPLS does and so on, or even forward at a specific bit rate. So if I want to control the rate at which a flow is forwarded, I can do that. Okay, so these are just examples of what OpenFlow supports. So it's basically a small set of primitives. It's protocol independent, and it's applicable to any device. Okay, so pretty much any device. So that's the whole point. They use commands that can be used by any device. So now this is the idea. So this is a controller, talks to the OpenFlow client. Okay, there is a flow table. Okay, and basically it says, okay, this is the wildcard, right? So anything, if it goes to this guy, if it goes to 5.6 or 7.8, that's the IP destination, then forward it to port 1, okay? So that's kind of the idea. Now here's the thing that, and so of course then you have these different ports that this client connects to.
I know the
I'm sorry?
This idea of packet classifiers.
Yeah, the packet classifier is at the switch.
Cheap level.
Yeah, yeah. So it's done in hardware, correct? Yes, yes. Okay, so again, this is yes, and so this is what I said, right? So forward packets, encapsulate, and forward blah blah blah. You can have any extensions you wish. Okay, so it's extensible. It's not it's just a matter of whatever has been defined by the OpenFlow protocol. Okay, so here's the and so this again it can look at pretty much every field. Okay, so this is an example of an IP field. Okay, so this is layer 4 source destination ports, IP fields, Ethernet fields, VLAN IDs, and so on. Okay, and so here's some examples. Suppose you want to do switching. Okay, switching means forwarding packets based on MAC destination address, right? So all you have to do is, if you match the MAC destination address here and everything else is wildcard, then send it to port 6, okay? Suppose you want to do flow switching, okay? Flow switching basically means look at up to the TCP source and destination port. So this defines a port, okay? And then if they all match, okay, they come on port 3 and they match all these fields, send it to port 6, okay? If you want to do a firewall, okay, firewall means you drop packets. So any packets goes to TCP port 22, secure SSH, secure login and all that, drop it, all right? So that's a way to do firewall using an Ethernet switch. If you're gonna do routing, routing means based on IP destination address. So I don't care about the other fields. If it matches these fields, then set it to port 6. Okay, you can do VLAN switching. Okay, if it matches the VLAN ID and so on, send it to these other VLANs. Okay, so set it port 6, 7, and 8. So you do multicasting there. Yes.
I can imagine the flexibility of the software I am dealing with, but I think it can fit for basic transactions. Okay, not sophisticated or complicated or large payload or even sophisticated real-time applications. In principle, it is the same idea proposed by Cisco in 2010 in networkers to replace traditional routers with servers like the DNS concept. Okay, so I can understand this, but in fact, replacing the proprietary hardware and the embedded systems and embedded software with functionalities raised on or residing on a separate machine with a software is additional delay. So in case of I am dealing with the exchange, stock exchange, it's impossible to apply this. If I am dealing with
my opinion here. I work at the Rouskas exchange. Okay, so
yes.
We were dealing with 80 million transactions per second.
Yes.
Okay, this is the exact number actually.
Yes, yes.
Okay, so yes, there will be some issues. There will be some overhead on the controller.
Yes.
But there are ways to deal with this. For example, I mean, probably this architecture thing is still experimental. It's still prototyping.
Yes, yes, yes.
So maybe not at its current form, but there are ways. For example, we could move the controller at a little bit behind, and then we would have some other micro, like controllers of assisting the controller to handle
Yes,
this.
even there is a proposal for using FPGA on that. Okay, so I do understand this, but in fact, still you are bounded by the flow control mechanisms of the Ethernet that should submit the requests to the machine. So if I am encountering any problems related to this connectivity, or the software for some reason is unreliable, or the hardware is not clustered properly and the software is not clustered, then I am in a trouble. So this is
Right. So yeah. So there's a couple of things I want to say here. So one is that obviously this is relatively new. Okay. This is not going to replace customized systems built for specific applications tomorrow. Okay. This has been
Exactly, not tomorrow.
right. Yeah.
Because they allow you to actually, I think the biggest advantage here is the openness. I
Right,
So if you
right.
want customization, you can actually build it by yourself. That's the
Yeah.
biggest advantage of the architecture that I can see.
It's a typical, let me
You can-
complete also. It's a typical example of what we teach to our students in the networking, how to design a virtual switch, how to design virtual router,
Mhm.
design with complete functionality, okay? The main concern here is how to deploy it on industrial basis. This is my concern.
Right. So right now, this technology has been very popular for relatively small general purpose networks like campuses, right? So you probably have a VLAN in this building, right? It will be very easy to replace that VLAN with something like this, and then simplify the management and everything. Okay, now, as the technology matures, I'm sure it will become better and better in handling more specialized cases. You know, obviously, you know, so, you know, Microsoft used to say that, you know, don't buy Linux because it can support the things that we do, right? But, you know, look at what Linux is today. So, I mean, it's running most of the servers, you know, web servers and all that. So, I think it's, you know, I'm not saying it's going to replace all the, you know, if you really need a Watson type of application for whatever you do, then it's very difficult to replace that with a, you know, open cluster, okay? Yes. It's a research, yes, exactly. So, but this is an interesting area of research about things that may become possible in 5 years or 10 years. So that's the whole point. But this is definitely an area that has been attracting a lot of interest in the last 3 or 4 years.
I'm afraid we have to maximize the hardware. We have to increase the number of processors, number of cores on the machine, such that I am faced that I need another architecture like the router.
Mm-hmm.
You understand?
I understand what you're saying, yes, yeah.
I would like to raise a point here, please.
Sure.
Stuck to the main idea, we would like to separate the control part, the data part.
Yes.
This is the main idea
Mhm.
of the SDN network. Dr. Hussain, you are talking about something else. The other guys, they said, okay, what is the difference between this approach and the traditional networking? Okay? They have to understand putting the control part in the network make problems. We have to make it memoryless. We call it bufferless systems in that case. I tackled this problem 20 years ago, and we published 2 papers in 1984. And then I can forward this because I implemented in that case a prototype of the SDN network, but the name is not just very new. I implemented a complete network, okay, using C language and Intel Z80 microprocessor, but the ideas which Dr. George talked about, it is new. You can modify if you like, or you can add your own. You can say, no, I don't agree about this. All the companies now, they try to build something in order to sell it for the public. And if you have something new, you can do it as well. And thank you.
Yes,
This is
we
my
agree.
comment.
That's the idea. It's more clean architecture.
Yes.
Forge.
And so this is the benefit, right? So the benefit is that if you want to do something new, right, all you have to do is write code, compile it on the PC here, the controller, and let it run. That's it. It's just a matter, it's very simple. So, you know, you can try 100 different ideas, maybe 2 of them will be really good, you implement them, right? But the point is that if you are in the old model, trying 100 ideas is impossible. You have to, you know, it takes a lot of time. So that's the point here. So there's a lot of issues, okay? So obviously, George said this is I think you said it, right? So there's a single point of failure, right? So you could go to a distributed control where each controller is responsible for a part of the network, okay? Or one controller is a backup for another.
Yeah,
Yeah, within reasons. Yes, right. Correct, of course. Yeah, yes, of course, right. So yes.
Some sort of replication should be there.
Yes, of course. Yes, yes. So again, you know, what is the right degree of replication? You know, that's a research issue. It of course depends on many things, including the size of the topology, your reliability requirements, and all that.
And it should need also a hierarchical level of authorization,
Yes.
such as authoritative.
Correct.
route to propagate.
Yeah.
the control directed to the wall.
Yes. Right. Then, you know, whether you should do on a forwarding on a per flow basis or over aggregate flows. Well, you know, if you can do flow based, I mean, the granularity is there. It allows you to do that. You have to exactly match the flow entries. The problem is that it will explode with the number of flows. Okay, and so for a campus network, right? If it's a relatively small network and you want to do you know, fine-grained control, that's fine. But in a larger network, it's not possible to do that, okay? And so basically you can have wildcards like I showed you earlier that covers large groups of flows, okay? And so now your flow table contains only one entry per category of flows. And so if you have a larger metro size network or map, then this is better, yes.
I have a question.
Sure.
In intelligent routing mechanisms,
Mm-hmm.
it will be based on bandwidth, delay, reliability, maximum transfer unit, and load. So switches or routers can exchange data among themselves to estimate these parameters, okay, and start getting the optimal composite metric regarding the routing.
All right, okay.
In fact, in this scenario, I will not be able to estimate.
And I think I missed that part here. Where is it? So there is.
Should I submit this data?
Yeah. So I'm trying to find out. I think there was a slide that I had there. I'm trying to find out if, or was it? Okay. Yes. So you have statistics. So each switch by itself collects statistics.
Yes, but I am talking about intermediate ops.
Yes.
I have statistics for end-to-end.
No, this is for the switch. So the switch then will convey that information to the controller, and the controller will have the statistics for any path that it wishes. So I'm actually, I have, okay, I think there is, let me see. Yeah, so this is, for instance, you can do load balancing, okay? You program the switches, okay? And then you collect the statistics. And based on the statistics you collect about the loads on each link in the network, okay, because you can correlate, you know the topology, right? So you get the statistics for this switch and the switch before it, and then the switch before it. So you can correlate. So now you can write your application centralized manner, right? It doesn't have to be in a distributed manner. You can correlate, and then you observe the load patterns. Then you say, oh, okay, let me do some load balances. So you change the routing, and then repeat. Okay, so basically, yeah. So you can do that.
Thank you.
Okay, so now, is it reactive or proactive, right? So the reactive means that the first packet of the flow goes, so the first packet of the flow, the switch hasn't seen it before, and so it doesn't match anything. Then it goes at the very bottom entry and says send it to the controller. So now the packet goes to the controller. The controller there will do the classification, decide how to route it, okay, and then will tell the switch how to forward that flow, okay. That is efficient use of the flow table, okay, because you don't use a table entry until you need it, okay. But of course, then each flow will have an additional time for setup because the first packet will have to be directed to the controller. Okay, there's another issue. If you don't have pre-installed entries and you wait for the first packet to install the entry in the switch, then if the controller goes down, your network goes down, right? Because any new traffic will not be able to be forwarded. Okay, a proactive, you pre-install the flow tables, okay, so there is no setup time, okay, But then, if you lose the control connection, then that does not disrupt the traffic because you can still take that, okay? But then you require aggregated flow, aggregated rules, okay? And of course you lose control, so you don't do it on a per flow basis. So typically there's going to be a mix of things. You're probably going to have some pre-populated, and then for flows that need special treatment or are unknown, you may actually have to go to the controller. I talked about load balancing, right? So you basically have a feedback loop here. You set the flow table entries, you collect the statistics, look at the loads, and then you can do load balancing and so on. And then another thing that you can do is network virtualization, right? How can you segment your network to implement specific virtual topologies? Well, this guy has the global view, right? And so now you add a virtualization application that says, okay, let me take this physical topology and build whatever virtual topologies I want. And so you build these virtual topologies, and then you instruct the switches to implement those virtual topologies, okay? So you can do any kind of topology here, any kind of virtual topology that you want, and you basically segment your network based on the flows, based on your customers, based on whatever rules you wish. Okay, so that's the end of my presentation, and if you have any questions, I'd be happy to, or if you want to discuss offline, that's absolutely fine with me. But the point here is that, you know, this is a new, relatively new technology, and there's potential for a lot of you know, there's a lot of research, open issues that can lead to, you know, good contributions. Hopefully, in the next few months, you will get the funds to build the SDN testbeds, and then you will have a testbed where you can actually, you know, very easily build applications like these. You know, so one of the issues that we have when we teach, let's say, you know, there's the research issue, there's a teaching issue, right? When we tell the students to build a protocol, they have to build in you know, we can't just tell them build a new routing protocol, right? You actually have to implement it in a distributed manner. That makes it difficult to teach networking in that sense. This makes it very easy to teach networking, okay? Because once you have the controller there, all you need to tell your students to do is implement these routing algorithms or any other algorithms at the controller, much easier to do and test in a relatively large scale than having them to implement only on 2 or 3 machines where that's really a toy network. Yes?
Will the existing switches be useful if we remove the logic IUS from them and reprogram the IUS and
Yeah.
again upgrade the firmware?
Yeah, yeah.
We have to change all the switches.
No, you don't have to change the little switches. All you have to do is install this open flow client. Yes, but hopefully, you know, the hardware that we will be able to buy with these funds will be for switches that already have the open flow client installed, so you won't have to do anything.
Does it need only to install the open flow client or disable the IUS which is existing?
So I believe the way it's done is that once you install the open flow client, that takes over, and so that basically completely disables the existing control. Yeah, yeah, right. Yeah, because then the connection is between the open flow clients and the controller, nothing else. Yes. Yeah.
I guess the trend applying the SDN is to hybrid between the existing networking nowadays with SDN by segmenting the network and making SDN working between the segment of the network, not within the segment itself, in order to save the investment of new technology and so on. But even in the segment, it can be used even within the segment. Why?
Yeah, within the segment, not between segments. This is within the segment.
I guess some switches doesn't support open flow client.
No, you can install the open flow client. That's the right point. Yeah, yeah, for existing switches. Yes, yes. Mm-hmm. Yeah.
Actually, another. What's about the economical visibility
Of this? because the switch is, so basically, have a very simple switch is much cheaper than buying a switch with all the operating system and software that comes with it, right? So this is much more, much less expensive than any other networking, which is why it has been adopted widely in relatively small networks. In fact, okay, it's not just small networks. The Google network that interconnects their data centers is built completely using SDN. Okay, so Google actually had a paper in SICOM